we've defined the equations of our model, that is the equations to get up till the hidden layer and to come down from the hidden layer to reconstruct the input. What we ought to do next is to define a cost function. This will be evaluating how well or how badly our model is doing. So for an autoencoder, the most natural cost function would just be to see the difference between the reconstruction and what was shown on input. So we'll call it cost underscore reconstruction. We'll calculate this in an L2 norm sort of a way. So what we'll have is x underscore row minus recons. So we'll have to take the transpose of reconstruction because it's a column vector. The square of this. And we'll be summing this over the axis that represents one visible sample. And when we take the mean of this across all the samples shown in a mini batch, we'll have the final cost. Now this is the most natural way to see how well or how badly your autoencoder is doing. Apart from this, many times in the final cost function, several other terms are tagged along. These are not exactly to evaluate how well your autoencoder is doing, but they're more like some prior what should I say, some prior knowledge, or not knowledge, well, some prior criteria that you want your model to meet in terms of its parameters, and they just evaluate how well the parameters are meeting those criteria. So apart from the reconstruction cost, you also have these terms. We can try to justify such an approach. So if I call the reconstruction cost a primary cost in some sense and the others as secondary costs, actually they're called regularizers. What happens with a primary cost is sometimes it is not enough to guide the gradient descent algorithm to a good minima. So you can imagine in such a non-linear system there being present many minima, and some are just not as good as others, that is their local minima. With the primary cost, now this is a justification or an aid to imagination rather than an actually rigorous statement. What you can imagine with a primary cost, that if you get stuck in a local minima, there is no easy way out for the gradient descent to other minima. That is, you can imagine there being small basins within which gradient descent can just get trapped. What these secondary costs do is that they change the nature of the landscape. They make a lot more parameters unfavorable by imposing on them their own constraints, that is the constraints of these secondary costs. And by making these parameters unfavorable, they help gradient descent to move easily from an unfavorable parameter to a more favorable one. One such cost is the sparsity cost. Now in studies of the mammalian visual cortex, they found that in the V1 region, a lot of cells display sparse responses. That is, if you show a bunch of visual stimulus to the brain and you just keep looking at one cell, you'll find that it shows a positive response for only a handful of cases. So this is seen as a justification for sparsity being a useful phenomenon in some sense. Well, not useful, as sparsity being a working phenomenon. That is, they found it to work in the mammalian brain. So why not try it in our computational models? So what we'll be intending to do is the responses that arise when we see a visual stimulus, that is our hidden layer, we'll want it to be sparse. Now such constraints have already worked well in machine learning, for example in the field of sparse coding. So it might be wise to add them to our models here. The way we'll do this is we'll first measure the mean activity. So I have not defined cost sparsity yet. For cost sparsity, I'll need a mean activity, which is just a mean over the responses of a particular hidden unit when I show it a mini batch. this is over a mini batch. So the way I'll be imposing this sparsity cost is, I'll say there is an ideal sparsity which I'll call rho. That is, if you take the average of the responses over a bunch of visual samples, you'll find that each hidden unit on an average gives this value as its average response. So I'll be checking deviations from this average value, from this ideal value, and I'll be penalizing them as a cost sparsity. So for that, I'll need to define a function here called a function here for the cross entropy. Why something as weird as the cross entropy? Well, these responses and these averages are seen as probabilities of activation, and what we are going to check is the difference between two sets of probabilities. So these are binomial probabilities, that is what we are asserting with our statement rho equal to 0.05, that our ideal model is on only 5% of the times, that it's on only 5% of the time, and 95% of the time it ought to be off. So when taking the distance between two probability distributions, it's natural to use something like the cross entropy. Apart from that, cross entropy has been shown to have quite a favorable gradient term, as in if you calculate the gradient of the entropy cost with respect to the parameters, you'll find that it is more conducive to faster descent. So let's define our cross entropy. So I'll do it with a lambda term. Cross entropy is equal to lambda. It will take in two inputs A and B and calculate the cross entropy as minus A into log of, so these will be tensor variables, so we have to take a t dot log minus 1 minus A into t dot log. Alright. So cost sparsity can be seen as a cross entropy between rho and the mean activity. And because cost sparsity gives the sparsity cost for each individual unit in our hidden layer, right, across a mini batch. So when I take the when I add it to my cost term, final cost term, I should be taking a mean of it. So you see the two means here for the cost reconstruction and the cost sparsity are pretty different. The reconstruction cost here is being meaned over different samples, as in image 1, image 2 and so on. Whereas the sparsity cost is being meaned over different hidden units. It was already meaned over different hidden units earlier, right? When I took the mean, it was already meaned over different images earlier when I took the mean activity. So with that we have defined our, so this is cost sparsity. With that we have defined the cost functions that we'll be using for our model. So what we've done till now is define the series and sets of computations that are involved in our autoencoder model. The next step ought to be to connect the unknown variables that are there in this model, for example the X row, with the actual data that we'll be giving to the model. So you can imagine what you have done till now as defining a computation graph, as laying out a computation graph similar to writing the body of a function in programming. And what we intend to do now is to write an interface that connects the variables used in that function's body with actual data. That is a sort of an argument list for that particular function. Keep in mind these are just analogies. So first of all, let us start with the validation function, because it will be a little simpler than defining a training function. The purpose of the validation function is to evaluate your model on a set of examples that it hasn't actually been trained on. The way we define a function is by using Theano's function statement. It has two necessary requirements. The first is the inputs and the second outputs. So we are sure that our outputs ought to be the cost variable, that is we'd like to see how well the model is doing on the validation function. As for the inputs, we ought to be giving it the x row variable. Right. Similarly, apart from seeing the cost on a set of validation examples, we'd also like to see how well our model is reconstructing these samples. So that will be a very visual evaluation of our model. Give it some samples, just see how well or how much without noise it reconstructs them back. So we can do this by defining reconstruct validation. It's another function with the same inputs x underscore row and the outputs as recons. I seem to have forgotten what my reconstruction variable is called. Yes, it's recons. Now the validation examples are already present in the form of a Theano type variable, that is a shared variable and it's called a valid variable upstairs. So what we'd like to do is just replace in some sense x underscore row with this valid. Theano function gives us a facility to do this by giving us a parameter called the givens. Givens is a dictionary where you give the parameter, where you give the variable to be replaced, which in our case is x underscore row, as the key, and the value as what ought to be replacing it, which in our case is valid. So we can copy this for reconstruct validation as well, and we have defined our two validation functions. The next step is to define a training function. So a train fn is a Theano function. As an input, it ought to take x underscore row. As an output, it ought to give us the cost. We are not looking at the reconstruction error on the training set till now. Similar to above, we can connect x underscore row to the training set. However, what we want to do is train in mini batches. We don't want to connect x row to the training set to the train variable as a whole, but we want to connect it to sub parts of it which are of size a mini batch. So let us define some variables so that we can do this. So first let's make an index variable. It's a scalar so that error messages are easily read, can be read easily. We'll give it a name index. Its d type is int 64. And now instead of taking x underscore row, we'll take index as the input. And similar to the givens dictionary above, what we'll do is we'll connect x underscore row to train, but we have to connect it to a mini batch. So let us also define our mini batch size here. Let's keep it as 128. So train runs from, so we connect x underscore row to train, to the part of train running from index into mini batch size to index plus 1 into mini batch size. Let's turn word wrap on. So if you have a look at the train underscore fn so far, what we've said is that we like to connect x underscore row to a chunk of data, and we'd like to see the cost on that chunk of data. We haven't actually put in the statements that will train the model in. So for that, we need to look into two concepts of Theano, that is automatic differentiation and the updates parameter of the Theano function statement. First, the automatic differentiation. Theano is a symbolic framework. That is, if you define a series of computations to get Vn, variable number n, from variable number 1, Theano has the ability to manipulate these computations in a symbolic way to actually give you the expression for the differentiation of V1 with respect to Vn. To make this clearer in our context, what I mean is, suppose you define cost as arising from using W, V bias and U and H bias in a series of equations, right? So cost is your ultimate variable and these are your starting variables in some sense. Then you can get the differentiation of cost with respect to W, and you can get the differentiation of cost with respect to V bias, and you can get the differentiation of cost with respect to H bias. This is because of the symbolic nature of Theano. Oh, by the way, if it is not clear, you can get this differentiation by Theano, as in you don't have to sit down and calculate what are the expressions required and how to invert individual steps in the computation graph yourself. Theano does this for you by uh, Theano does this for you in an automatic sort of a way. Secondly, suppose you do get these expressions, you do get these expressions for the gradient. How will you be inculcating them into your train underscore fn? Now, Theano.function provides a facility for you to give a set of shared variables that will be changed every time this function is executed. That is, if you make a train underscore fn, you can also define a set of variables which in our case ought to be W, V bias and H bias, that ought to be updated or modified every time this train underscore fn is executed. The way we do that is by the updates parameter. So we can write updates equal to, let's say, a variable we have not defined yet, train underscore updates. The type of variable train underscore updates will be is an ordered dict, which is available from the collections module. From collections, import ordered dict. So now we need to make this train underscore updates and actually populate it with the relevant updates for each of the parameters. So let's first initialize it. Train updates is an empty dictionary. A typical form that train updates will take for any of our model parameters, for example W, will be train updates of W is W's current value minus a learning rate into grad with respect to W. So this grad with respect to W is the gradient of the cost with respect to W. LR is a learning rate. This is a typical gradient descent sort of a learning rule. We could just write LR as a constant here in this expression, or we could define LR as a Theano variable. So LR would be a T dot scalar of the name LR and a D type float 64, let's say. The difference between the two approaches of defining LR as a Theano variable and defining LR as a constant here. So what I mean by a constant is just by writing, let's say, 0.01 here. But I'm saying that I don't want to do that, and why I wouldn't want to do that is, suppose I wanted to change the LR in the course of my model being learned. I might want to do that. That many times when we see that the validation error is sort of flatlining, we decrease the learning rate and it starts decreasing at a much faster pace again. Anyways, so the point is that we might want to change LR in the course of our learning. So if I have defined LR as a constant and I have made a train underscore fn like so, I wouldn't be able to modify this LR without actually having to rewrite the code here, without actually going inside and changing this statement let's say this was 0.01, and actually changing this statement to 0.001, let's say, and recompiling train underscore function. So if this is not clear, what I'm saying is, for the time being, let's take LR to be a Theano variable, right? So train underscore updates for a parameter ought to look like this. So I have defined an LR that would be appearing here. Let's write out the gradient with respect to W. So this is where the automatic differentiation will come into play. So we'll have T dot grad of the cost with respect to the parameter. Now this gradient statement takes as its first argument the function you will be differentiating, and as its second argument the set of variables you'll be differentiating with respect to, right? The first argument necessarily has to be a scalar. Many a times I've had the error of accidentally differentiating something like, let's say, cost sparsity, which is not a scalar but a vector, and getting the error t dot grad's inputs first input ought to be a scalar. So with this we see what a typical training update ought to be like for a model's parameter. I like to do this for V bias and H bias. I could copy and paste this and change W to H bias and V bias everywhere, but instead let me first define a params list which contains all the model's parameters W, H bias and V bias. I loop over this for P in params and get the gradients with respect to each param and put it into a training update for that param. So grad with respect to param is T dot grad of cost with respect to P, and train updates of P ought to be P minus LR into grad with respect to param. So I seem to have removed LR from here. So let's define LR again. And so I have defined the training updates that will be needed for my model. Oh, I forgot to add in U into this list. So let's do that. W comma U comma H bias comma V bias. Now good thing that you reminded me of U. So many times you hear of autoencoders with a special feature called tide weights. By tide weights, what I mean is that the weights for the upward pass, which for our case are W, and the weights for the downward pass, which in our case are U, are connected by the relation that U is equal to W transpose. So what this does is, it reduces the number of parameters that are going to be learnt in the model, which is usually a good thing because it makes gradient descent work better. There are other reasonings for this as well, in terms of template matching and a dictionary for reconstruction, but we won't go into those right now. For our first model, what we'd like is to have this constraint that U is just W transpose. So we'll add this via a given statement. Oh, we already have a given statement, so we'll add it to the givens dictionary as U should be W dot transpose. With that, we have completed the definition of our training function. In the next session, we'll make the main loop for training this, which will also include parts for gathering information about the progress of training, that is the usage of the validation underscore F1 and the reconstruct validation functions. So see you then.